In this video, we're going to first want to talk about what the domain of logarithmic functions are, and then we'll give a few examples where we have to find the domain. Okay, so first thing I want us to notice is, I wonder if any of you guys have already picked up on this, that the function f of x is actually an inverse function of g of x, which is a to the exponential. So log is the inverse function of the exponential, right? I mean, okay, so like, if this doesn't hit with you immediately, remember how we find inverse functions? So the first thing, let's replace. So say I'm trying to find the inverse function of y equals log a of x, right? Okay, so the first thing you would do is you would replace x and y. All right, and then you would solve for y. Now to solve for y, I would say, okay, so the base is a, and the logs equal exponents, so this is the exponent, and this equals y, right? So the inverse, so if this is f of x, right, then the inverse function would then be g of x equals a to the x, right? So log and exponential are inverse functions of each other. All right, so what does that mean? Why did I just go through that? Well, the domain and range of inverse functions are basically flipped, right? And we already know the domain and range for an exponential function. So the domain for an exponential function is negative infinity to infinity. And the range for an exponential function is 0 to infinity, because remember we had that horizontal asymptote. Okay, so that means then, so if we flip those, we talk about the domain and range for the log function. The domain will be whatever the range is for its inverse function. So it'll be 0 to infinity. So the domain will be 0 to infinity. And the range then will be negative infinity to infinity, which matches the domain. Okay, so what does that mean? What does that mean? The domain is 0 to infinity. Well, that means that this x, whatever you're taking the log of, needs to be more than 0. Okay? And the reason why it needs to be more than 0 is because, let me go ahead and write this down here. So f of x equals, I'm going to go ahead and use the y. So equals y equals log base a of x. So if I were to rewrite this in exponential form, so it's base a to the power y, right, logs equal exponents, equals x, right? So this is not the inverse, this is actually what, the log of a of x, these two statements are identical, right? So this is not the inverse, this is just, these are two identical statements. Okay, so the domain is 0 to infinity. Well, what is that? That means that if we take a positive number, so a is positive, and we bring it to a power, we can never get a number that is smaller than 0, right? So, if you take a number like the number 4 and you bring it to the power 0, well, that's 1, right? And then if you take the number 4 and you bring it to the power 2, then that's 1 over 16. If you take 4 and you bring it to the power, 4, then, well, let's see, what's 4 to the 4? So that would be 1 over 256. Okay, so it's getting really small, and we can even make it even smaller, but it's never gonna reach 0, right? So whatever I have in for x, it needs to be more than 0. All right, so let's go ahead and do a few examples where we need to find the domain of log functions. Okay, so here we go. We know that x minus 3, so whatever you're taking the log of, must be more than 0. Okay, that's basically what we just said in the previous slide. All right, so let's go ahead and solve this. X is greater, so I add 3 to both sides. X is greater than 3. All right, so then what's our domain? Our domain then is 3 to infinity. All right, let's go ahead and do another example. All right, in this example we have, all this stuff, this rational expression here, rational term, that all must be greater than 0. So x minus 5 over x plus 1 must be greater than 0. So whatever you're taking the log of, it must be positive, right? Okay, so now Now, if you were to go about and try to solve this, and if your first step was to, I don't know, multiply both sides by x plus 1, and then you had x minus 5 is greater than 0, you would be, don't do that. That's not right. Okay? Now, if you remember from inequalities, the way that we went about solving these sort of inequalities was using test points. Okay? So what test points do you choose? Well, let's go ahead and find like zeros and areas where this is not undefined, right? So x minus 5, if we were to set this equal to 0, x equals 0, or sorry, if I were to add 5 to both sides, x equals 5. When x equals 5, this equals 0. Okay, so that's an interesting point that we want to look at. And then another one is x plus 1. It's fine when that equals 0, so x equals negative 1. Okay, so the function is undefined there. So let's go ahead and start doing our test points. So x, and then I'm going to write here x minus 5 over x plus 1. All right, and let's see the test points. So I have negative 1, where this is undefined, or NA, and then I have 5 where it's 0. Okay, so I want to see what's happening, in the areas around these two numbers. So say, for example, negative 2. So just any number that's less than negative 1. And then a number that's between negative 1 and 5, say 0. Could choose any number. And then say 6. Okay, so I'm really actually just interested in the sign of this when when x is less than negative 1, for example. Okay, so I don't really care what the number is. I just care about the sign. So negative 2 minus 5, that's going to be a negative number. And then negative 2 plus 1 is also a negative number. So this is going to be a positive number, right? And then 0 minus 5 is negative, and then positive. So this one is going to be a negative number. And then lastly, 6, if we plug in 6, we would get a positive number divided by a positive number, which is positive. All right, we were looking for when this function is greater than 0. So we're looking for these areas when it was positive. All right, so when is it positive? It's positive left of negative 1. Okay? And then it's also positive more than 5. All right, so left of negative 1 and more than 5. So there you go. This is my domain.